Welcome back to Computer Metanoia. We are actually studying the first chapter of digital electronics, which is the representation of Boolean functions. And we were discussing about representing a real life problem into a binary digital system and to a truth table. So we are actually understanding an example. We will be actually understanding the process using an example that I have taken over here. So if you see the problem statement of a real life problem, which we have to convert into a binary digital system, then if I read out this particular problem for you, then in simple words, it's nothing that we have two managers whose names are say X and Y. And those two managers are given powers to take up decisions. Now, there are some rules by which they have to take the decisions. Now, in a particular day, the attendance of this particular two managers, X and Y, can be anything. Like in a particular day, both of them are present. In a particular day, both of them are absent. In a particular day, X is present, Y is absent. In a particular day, the reverse is true. That is, Y is present, X is absent. So these are the four combinations that we can have definitely. And we have been given that manager X can take a decision even if manager Y is absent. But the reverse is not true. That is, if manager X is absent, Y cannot take the decision. So using this particular statement, this particular thing as a problem statement, we have to design a binary digital system. Simply, we see that we have two particular managers. So if we straight away go to the binary digital system, and here if I want to represent for the input side, if I consider 0 means absent, 1 means present. In the output side, I can say that 0 means decision can't be taken, and 1 means decision can be taken. So simply what this means is that in the input side, we know that in a truth table we have two sides. One is the input side and one is the output side. So in the input side, I will represent 0 if either of X and Y are absent or something like that. That means if a person is absent, I will represent it using 0, and a person is present, then I'll represent it using 1. On the output side, on the other hand, what we are actually deciding that whether the decision will be taken or not. So here I will represent 0 as decision cannot be taken, and 1 means decision can be taken. So now if we observe that we will have um, the input side and output side. So in input side we have two managers X, Y, and in the output side, this is the output side. Let us represent it using F. So what are the combinations of input and present and absent scenarios that we have? The first scenario is that both of them are absent. The second scenario is that X is absent, Y is present. Third scenario, X is present, Y is absent. Final scenario, both of them are present. Now, according to the problem statement, definitely if both the managers are absent, we cannot take the decision. Now, the statement says that if manager X can take the decision even if manager Y is absent. So manager X is present, Y is absent, the decision can be taken. But the reverse, where X is absent but Y is present, it's not true. So this will be represented using 0. And it has been said that if both managers are present, the decision can be taken. So both of them are present, we can take the decision. So this is the basic representation of using a table. That means we can read it as if X is absent, Y is absent, decision can't be taken. If X is absent, Y is present, decision cannot be taken. X is present, Y is absent, decision can be taken. Both of them are present, decision can be taken. So this is the basic representation of a particular scenario. This is a problem statement that we have represented using this. Now, You might ask that how will the circuit look? We are not actually going into the details of it, but basically we will have a circuit something like this. We will have two inputs X and Y, and we will have a binary digital system, that is a system which will decide. This is a binary digital system, and here we will get the output F. So this binary digital system will actually take care of the logic. That means this particular logic that we have, it will be designed according to this particular what should I say, the truth table, and it will be designed accordingly, and accordingly we will get the output as this if the input are these. Now you can understand. Let us take our discussion a step further. Now you can see that here we have four scenarios. That means we have two managers. For two managers, we will have four scenarios. So basically what we see is that for n number of managers, we will have 2 to the power n number of possibilities. On the other hand, for 2 to the power n is equals to m, log base 2n number of possibilities. I did a mistake over here. For n possibilities, we will have log base 2n number of binary digits, the binary places basically. So we have four possibilities. So for four possibilities, we will need log base to 4, that is two number of binary digits to represent this particular problem. The reverse way, if we have two binary digits, we can represent four situations using that. Similarly, if we have say eight, eight of these situations that can be thought of. So we have eight different situations. So if we have eight different situations, we can use log base to 8, that is equals to 3 binary digits is enough to represent this particular situation. On the other hand, the reverse way, if we have three binary digits, we have three columns of input, then we can represent eight different situations. So basically it takes place in this manner. So that's all from the binary digital system that we have. Now we will be actually learning how to represent this particular output column using the input column. We have two approaches, the min terms approach and the max terms approach. We will be actually understanding them in the next particular video. So that's all from this video. Please stay tuned, and if like the video, if you liked it, and share with your friends, subscribe to our channel, and keep learning. Thank you very much.